Hi folks, so last time we were talking about electronic systems and we were talking about passive components. So this time we want to move ahead and talk about active components. So we're going to call this building blocks part 2. So we're thinking about active components, and of course we're going to need semiconductors, and semiconductors, of course, you're going to remember back from chemistry, are going to be coming from group 4 of the periodic table. And so we've got silicon and germanium, and we'll also need cadmium sulfide. Now silicon is the one we're going to concern ourselves with. That's the common one that we're always thinking about. So when we think about silicon, and we think about silicon in a crystal, and let's assume that this is 100% pure silicon, which of course we're never going to really achieve, but we've got silicon, and it's in the middle there, and it's got these 4 atoms of silicon around it. And you notice that we've got those green dots and those red circles, and those represent electrons. And so thinking way back to chemistry, you know that your silicon has got 4 electrons in that outer shell. And then when we put those 4 silicon atoms around the central one, then the central one is going to have its own 4, and it's going to borrow 4, and so it's going to have 8, and so it's going to be happy. So that silicon in the middle is happy, and it's got all these electrons, and they are accounted for and in use. So that is our pure case. But of course, when we're dealing with semiconductors, we're looking at what happens when we're not in that pure case. And so when we're not in that pure case, we have these holes, and these holes are where there's not an electron. And so we can think about the holes as being a positive charge carrier. And so this gets back to, remember we were talking about Ben Franklin, and we were saying that there's that conventional current flow, but it's actually opposite from the electron flow. Well, that's what we're dealing with here. So we can think about this hole, or this positive charge carrier, in this case moving to the right, but you know really that's an electron moving to the left. Either way, it still works. It's just saying the same thing 2 different ways. So we've got these holes moving to the right, we've got the electrons moving to the left, and so we've got charge moving around through our material. So what is that going to do for us? Well, we start thinking about doping. Doping is when we're taking our silicon and we're adding something else to it, right? So we've got, in this case, N-type doping, where we have added a donor element. And in this case, we've got 1 extra electron that's now moving around through the material. Everything's happy except for this 1 electron moving around. We call that N-type doping. Alternatively, we can have P-type doping, where we have doped with an acceptor element like aluminum, boron, or gallium. And now we've got a hole. So we're short on electron. So we've got this hole moving around. And so I think you can see with the N and the P that we're talking about negative and positive additional charge moving around. So we can create N-type and we create P-type materials. So of course, what happens is we are going to stick them together. So when we stick them together like this, we've got a junction of a P-type and an N-type material. And so we put them together and we call it a P-N junction, which I think stands to reason. We've got the P and the N jammed together there. And so on the one side, the P side, we've got a bunch of extra holes because we were adding these additional acceptor elements. And on the N type, we've got a bunch of extra electrons because we're adding those donor type elements. And in the middle, we don't really have either of those. We have this region that falls between them that we call the depletion region. And so we call one side the anode and one side the cathode. And hopefully you look at this and you say, aha, I've seen this sort of thing before. Because of course, this is a diode. So when we think about a diode is just a PN junction where we have an anode and a cathode. And because we have holes on one side and electrons on the other, you can see that we're biased to generate a current moving from anode to cathode versus the other way would be more difficult. So this is a diode, and just a little bit of trivia for you. When we talk about diodes go back to 1940 with Russell Ohl at Bell Labs. So the first diode was actually discovered in 1940 because Russell Ohl was working with silicon and he was purifying it. So current silicon that we use in semiconductors today is very pure, 99.999 something percent purity. But the silicon that Russell Ohl was working with was not as pure. And so he was using something that was only 99.8% pure, which sounds still really pure, but it's not the same as what we've got in fabs at Intel or AMD or wherever else. So his silicon chunk had a crack in it. And this crack was light sensitive. So when the crack was pointing at a light source, he would generate a little bit of a charge. And so this was a naturally occurring PN junction. The crack separated a P-type from an N-type that was just based on the impurities, which I find really interesting because that means that the first diode was not invented, it was discovered. It was naturally occurring. So there you go, we've got diodes. So when we think about diodes and we're thinking about electronics, we're thinking about an electronic equivalent of what our mechanical engineers might think of as a hydraulic check valve. So in this case, we know that fluid can flow one way from right to left, in which case it compresses that spring and goes around the ball and fluid flows, but not the other way because the ball closes off that orifice. So it's like a hydraulic check valve, and just like a hydraulic check valve, if you apply way too much pressure to this thing, you can break the check valve. And just like that, you can break a diode if you apply way too much voltage. So when we want to draw this out and see this graphically, we start looking at a plot here of the voltage and the current. And so we're looking at the voltage across the diode versus the current through the diode. And it looks something like this. And we'll mark off a couple of regions. You can see it's very steep on the edges and it's very flat in the middle. And so we'll draw in some lines here to mark off the steep parts versus the flat parts. And we'll label them. So the steep part where it's going negative is the reverse breakdown region. The steep part where it's going positive is the forward bias region. And the middle is the reverse bias region. And so we can certainly put in some numeric restrictions here. So we're saying that if VD is greater than VY, then we're operating in this part that we call the forward bias region. And you can see in that case, a little bit of voltage change corresponds to a lot of current change. And so we think of that as being nearly a short circuit. It's almost perfectly vertical, which would tell us that we've got infinite current available through there, which is a short circuit. If we're in that reverse bias region between VZ and VY, then you can see that we get almost no current. And in that case, we think of it as an open circuit. And so that's where it's not conducting. So those are the two regions that we normally operate in. Either we are short circuiting it or we're open circuiting it. And then certainly you could get into the region that we call the reverse breakdown region, but you can see in that case, the current goes very quickly negative, which is to say that we are potentially damaging it. So there are limits in which you operate this diode. You don't want to exceed the breakdown voltage because you can damage the diode. And certainly you also don't want to exceed the power dissipation available. So if you put way too much current through it, you could certainly cook it. So when we think about a diode, it's going to look something like this. We've got, in this case, a voltage supply, which is coming from a battery. We've got a diode, we've got a resistor. And so if we're operating in that conducting short circuiting region, the forward bias region, then it looks something like this. We've got the short circuit, but then we also have that little bit of a voltage drop across the diode. And that voltage drop is usually 0.6 to 0.7 volts. Alternatively, if we're operating in the reverse bias region, where we expect it to act as an open circuit, then it's just open and no current flows. So when you have a diode, expect to see a small voltage drop across it and either a short circuit or an open circuit. So if you're, let's see, so if you're thinking about this in terms of maximum current, you could put a current limiting resistor in there. So if we want to calculate the current through it, then certainly we can figure out what the maximum power dissipation is going to be. We can calculate the current through it. We can know the voltage drop across it, and we can work out, should we put in a current limiting resistor to limit the current. So when do we use diodes? Well, I'm going to show you a couple examples. So there are signal processing applications. There's voltage regulation. Indication is one that you've seen a lot in terms of LEDs, showing people whether something is happening or not. And then isolation is another interesting one that uses LEDs. So we'll start with signal processing. So rectification is this idea that we have an AC signal and maybe we don't want all of the AC signal. So if we've got an AC signal, we run it through a half-wave rectifier, which is a diode, and then run that through a load. Then what you would expect to see is that when the voltage applied to the across the diode is in the forward bias, we're going to see the short circuit behavior, and when it's in the reverse bias, we're going to see the open circuit behavior. So you would expect to see here that it's going to pass through positive and then reject negative. And so that's what we do see, is you apply a sinusoid, and it passes through the positive part, which is still going to follow that sinusoid, and then it's going to reject the negative part, just going to flatline because it doesn't conduct. So we get something like this. This is a half-wave rectifier. Notice that there is still a little bit of a gap up here, and that's our 0.6 to 0.7 volt drop across the diode. So that is our half-wave rectifier. We can also do a bridge rectifier. Notice that this one's a little more complicated. We've got more diodes in there. But you can certainly trace out the path. So we might see a path that goes through this diode and around and then through this diode. Or, let me change colors here. We might see a path that goes this way, through this diode and around, and then through this diode and back. And so what you see is that it's going through the load the same direction, which is to say that we are always going to end up with our positive part of our sinusoid, and then our negative part has flipped up to also be positive. And so we get the same sort of sinusoid, but folded up. And again, you get that 0.6 to 0.7 volt drop because we do have that drop across the diode. So this particular bridge rectifier scheme, you see this in AM demodulation. That's a good application of it, demodulation. We might also use this to specify limits on an incoming voltage. So if we have an input voltage, we might have two sources provided, some V big M and some V little m, and we've got diodes here. And so what you'll see here is that Vm, cap M, sets a maximum limit, and V little m sets a lower limit. And so our input signal is now going to be clipped at those based on the application of these sources with the diodes. And where might we use this? Well, the first place that I think about using it is in an analog to digital converter, because my analog to digital converter is going to be limited in terms of voltage. It might be plus or minus 5 volts. It might be plus or minus 10 volts. But either way, I want to protect my circuit from applying too high an input voltage. And so I can use diodes and supplies here to clip the signal so that I'm not bringing in a voltage that is out of range. Another application is a peak detector. What happens if you want to follow the peaks of this particular interesting waveform? Well, you can use a diode and a capacitor. And in this case, what you'll see is that the diode will allow the input voltage to charge the capacitor, and then the capacitor cannot discharge back towards the input, and so it just is going to hold the value. So you get something like this. It charges and it holds the value. So this is very fast. It's certainly faster than using an ADC with a microcontroller. And then it is also useful in things like radio frequency peak power measurement. You might see another version of this where you put in a couple of op amps. So I will draw those in real quick. And in the op amp configuration, we put in V in here. We'll tie that out to here. And so now we've got this follower after it, and we've got the input op amp as well. I took this from planetanalog.com. I thought they had a good explanation. So again, the input is going to charge the capacitor, and the diode is going to then prevent discharge of the capacitor, and it'll keep that peak value. Okay, we have very special diodes we call Zener diodes, and so these are operating specifically in that reverse breakdown region where things go negative. And the nice thing about that reverse breakdown region is that you can see, again, the voltage doesn't change very much. And because the voltage doesn't change very much, operating these in that reverse breakdown region is like using a voltage regulator. So why do we call them Zener diodes? Well, because Clarence Zener is the one that worked on these, and so he invented them in 1948 at Bell Labs, and we got to name them after him. So what's a Zener diode look like? Well, in the one case, it's forward biased, and in the other case, it's reverse biased. And so in the forward bias case, because it's got that very steep upward part, it's going to hold at VD. Sorry, not VD, that'd be VY, I think I called it. And then in the other one, it's going to hold at VZ. And so in either case, it's like acting like a diode with a voltage drop there. And so it should hold us very, very constant at those voltage levels. So where might we use that? Well, we might use it in something like a voltage regulator, that if you have an unregulated supply, then you can have a source resistor, and you can use this to regulate the voltage across the load. So you might, there's your unregulated supply, there's your voltage regulator, and so now the load voltage is going to be very fixed based on the reverse breakdown voltage of the Zener diode. So you might need to specify one of these. So if you want to specify it, then you know that the load voltage should be the drop across the Zener diode in the reverse breakdown region. And so you could calculate the current through the load, IL. So we know the voltage, we know the load resistance. And then we can also use that to determine the current through the Zener diode. And we know what the source current is because we know what the source voltage and the source resistor are going to be typically. And so then we could, just like we talked about before, we could calculate the power being dissipated by this diode based on the current through it and the voltage across it. And so based on the power, we could figure out if we have an appropriately selected Zener diode. So in this case, we have a very easy voltage regulator. So where might we see this? We might see this in something like a DC power supply. So if I have an AC voltage coming in, which there's our AC voltage, I might step it down through a transformer, so I get a slightly different voltage there. I might rectify it. So now we've got our bridge rectifier using diodes, and so we're going to flip it all up that way. We'll put it through a low-pass filter. That's some passive components we talked about before. Now, this is only a first-order low-pass filter. You could do something a little more complicated if you really wanted to, but that'll smooth it out. And then that slightly smooth one we'll put through our regulator, which could be just a Zener diode, and smooth it the rest of the way to go to the load. And so that is a very simple DC power supply from an AC input. Okay, and notice that this one also included two different applications of diodes and an application of passive components. All right, so LEDs, I mentioned we could use these as an indicator. You've undoubtedly seen LEDs before. It is a diode that emits light, and so the amount of light is going to be related to the current. And so we can certainly make them brighter or less bright based on the current. So if we have a switch, we might apply a voltage here, and we have the switch that is going to open and close, and it's going to allow the LED to turn on or turn off. So when we think about LEDs, there's going to be a voltage drop across them. The voltage drop is going to be related to the size and the color. I usually think of the red 3mm LEDs as being sort of a standard. It's about 2 volts. So somewhere in that range, 1.5 to 2.5 volts, but usually the red ones that I have in the lab are going to be a 2-volt drop. We are going to need to specify that current limiting resistor. And so how bright do you want it? We'll choose your resistance value appropriately, but you definitely want to have something in there so that you do have some control over the current going through it, because again, we don't want to exceed the power dissipation of our LED, or we could damage the LED. So when you think about plugging in an LED to an Arduino board, I think a lot of times I see people plug it in directly LED to a digital out to ground. Well, you're missing the current limiting resistor. Please do add a current limiting resistor. The LED Arduino you're probably not going to damage because the current output is so low anyhow, but it's always a good idea to include the current limiting resistor. So kind of the opposite of that is you got a photodiode, which is, again, that PN junction. This is the same one that Russell Ohl was using. And so it will generate a current when you get light. So in this case, we are applying light, and then based on the light intensity, we get a current. So light shines, current flows. Oops, advanced it too fast. So light shines, and then current flows through your resistor there. So if we were to combine these, we have a photodiode with an LED, then certainly you can have something like this where you apply an input, it generates light, that light goes to a photodiode, which generates an output. And so this is called an Opto Isolator or an optocoupler. And so now we have a non-contact connection between two circuits. There's no electrical connection there, it's only light. So if you want to connect high power to low power, this is certainly a way to do it. It's not going to be good for analog signals because you're talking things on and off. Going by intensity is probably not going to be a good idea. But certainly you can do relatively high power signals that are digital. So my notes here, I've got a note that you can go up to 10 kilovolts, which is quite high. So there we go. There's some applications of diodes. And we'll stop here and we'll move on to the next video.